Hello everybody. In today's lecture, we'll be talking about the various available techniques for converting a digital signal to analog one and vice versa. Now, I don't think I need to emphasize the effects of a digital world to a person who is listening to this video on YouTube. Nature has placed no restrictions on how I communicate with people around me, but science has created a virtual digital channel of communication. Now, which has its pros and cons, obviously. So nowadays, young people prefer chatting on a social platform rather than making the effort to go out and meet somebody. On the other hand, were it not for this medium, I wouldn't be able to communicate with you during this virtual curfew imposed by this CODV outbreak. Anyway, let's get on with the lecture. In section, we'll be talking about digital to analog conversion, and section 2, analog digital conversion. Now, before we proceed further, let me first of all define the terms. An ADC or analog to digital converter is a circuit which accepts an analog signal and converts it into a digital format. The digital converter does just the opposite. There's a circuit which is responsible for conversion of a digital information to an equivalent analog information. Now, what are these converters basically, and why do we need them? Basically, if I say it in a single sentence, it will be we live in an analog world surrounded by digital devices. Now, if you look at a typical signal pathway, say what I'm speaking or the sound which is coming out of my voice box, or say any real world signal like a thermocouple, is converted to a speech signal by the microphone I'm holding in my hand. Now that goes into a digital processor that's in the smartphone I'm using or the laptops. Now there, that works on a series of 1 and 0s. So what I need in between is an AD converter. So from my voice, a transducer, the microphone converts into the electrical signal that goes into the a digital processor that's converted to a digital signal and then goes into a digital processor. Now this digital processor is launched into, after processing, say amplification and filtering and all that, is passed on to a channel which can be a free space like in mobile communication, or you can use something like say an optical fiber. Now at the receiver end, there's again the digital signal is converted back to an analog signal by a DA converter, and then say an inverse transformer like something like say a speaker at your end, which converts that digital signal back to voice signal so it can be received by your eardrums. Now, so why do we need these digital devices? Now, see, analog signal basically is a continuous signal with infinite values in a given range, like say signals, sounds, images, etc., which human beings can process. From that goes by my vocal cord to the vibrations in your eardrums, because which you can hear what I'm saying. The digital signals have discrete values, say a on-off signal or 1 and 0. So why do we go for these digital devices? First of all, say I'm speaking to somebody. So my range of communication is limited to how far my voice will carry. Now, so if I need to communicate with a large audience, say someone who's in a different city or different country, then I need a communication system. And for that, I need a sophisticated system or a digital system. Again, say this class I'm holding, you want to hear it after say a day or a month, then I need to store this somewhere. Now again, so I need to store the communication views. So there again, digital devices come into the picture. Analog signals have certain limitations, like they need amplification to cover large distances. Then again, processing and security. Say a digital signal that has been transmitted over a space. So unless you have the required decoder, say the dish TV on your rooftop. Now, if you don't pay the subscription, you won't be able to see the channels. Although your dish TV or the dish antenna is receiving the channels anyway. So unless I have the proper decoding circuitry, even if I have the signal, I can't be able to decode it. So this is a security point of view. And another thing is cost effectiveness. Nowadays, with the availability of VLSI technology, these sophisticated digital systems are much easier to and cheaper to reproduce. The major digital limitation of a digital system, if you so say, is how accurately it reproduces my analog signal. Now, so first step, how to convert from analog to digital. The first thing which you have to do is you have to sample it. Now say in the signal, The given amplitude rate is divided into 15 levels. Now at each point of time, I take a sample, like say the sample, it's showing something like 5. Now for this one, although it shows a higher value, since at the point of sampling I'm getting something like say 100, that's the binary equivalent of E. So what I'm doing is, the first thing I'm sampling at a point of time, and the next thing is I'm breaking up the sample into certain discrete values, like say on a ramp, and say on the steps of a building. On a ramp you can stand at any point of time, at any point of the pathway, but on a step you can't stand in between two steps, something like that. And the last part is encoding, where these say 7 or 8 or 10, that's converted into a stream of ones and zeros. Now most analog digital converters require a digital to converter as one of their component systems. So what we'll do is we'll first look at digital to analog converters. Now DAC has general form, say a circuit like this. There are n inputs depending on the number of bits you are using, and it generates a corresponding analog output. The general form is something like that. V0 equal to K. You see the the expression in the bracket is something like, if you convert a binary number to base 10 number, then we get something like that. B2 was 0 into the first bit, then 2 to the power 1 into second bit, 2 to the 2 into third bit, and so on. So something like that. And this multi-factor K, it depends on the step size, step voltage. Again, it depends on the way we implement this digital to analog converter. We will be basically looking at two types of digital converter. One is a binary weighted resistor DAC, and second is the R2R DAC. Now let's look at the first one. Here you will see it's basically a sum or adder using an op-amp. The difference is given different resistors used in the adder are seen in order of the binary bits. So this 2 to the 0, 1. So 2 to the 1, 2 to the 2, that's 4, and 2 to the 3, 8. Now, if you since this point is virtual ground, so the current due to any input will be V minus 0 by the constant R. Now, so at any point, say we implement the voltage by something like Vk equal to Sk into V, where Sk is a binary variable, that is either 0 or 1, and V is the input voltage of VR. So for the kth input we get Vak minus V0 by Rk, that's Sk into VR by Rk. So S can be either 0 or 1, and correspondingly V equal is the input voltage. So if you sum for all of the voltage, we get something like this: S0 VR bar 8R for the first one, S1 VR bar 4R, 2R, RR, something like that. So if we do an LCM using the 8R, the maximum value, that's 2 to the n minus 1. We are giving 2 to the n minus 1 because see, this is a 4 variable system. So 2 to the power 4 minus 1, that's 2 to the 3 or 8R. So if you take an 8R common, what we get is VR by 8R. So this remains S0 VR. This becomes 2S1 VR. This becomes 4S2 VR, and this becomes 8S3 VR. So we get something like especially like this: Sk into 2 to the power K. That means S3 corresponds to 8, S2 corresponds to 4, and so on. And the output voltage that is due to the current flowing through this path, that's minus Rf into I. So it gets minus Rf into, or minus VR and Rf into ZH. So for a 4-bit system, we'll get something like this: V0 equal to minus Rf, S3 VR by R, S2 VR by 2R, and so on. And the output will be Rf VR by 8R, 8S3, 4S2, 2S1, and S0. So if we consider these as binary variables, so if we convert a 4-bit digital number to a base 10 number, we will get something like this: B0 plus 2B1 plus 4B2 plus 8B3. Okay. Now let's look at a problem. Say we have a 8-bit digital to analog converter. The problem is, it's said that if the maximum allowable current from a source, that's this one which is driving all the inputs, is 20 milliampere, find the minimum value of resistance required for a supply voltage of 5 volt. Also find the resolution. The resolution differential will be coming to later. Now the maximum current will obviously be drawn when all the inputs are locked to supply voltage. That means when S7, S6 up, all the bits are 1. So you'll be getting an input current from that VR by R, VR by 2R, and so on. So it's 1 by 2 to the power 7 VR by R. Now this sum 2 to the power 0 2 can be represented and can also be represented as 2 to the 8 minus 1. Like this, and something like say you are 4-bit. If you put the 4 bits has 1111, that corresponds to 7. Now that can also be written as 2 to the power 3 minus 1, right? 8 minus 1, 7. So something like that. So this 2 to the power 7 comes to 2 to the power 8 minus 1. Okay. So if you put the value, it comes like 255 by 128 VR by R. Now this VR is 5 volt as we have said. The I max is said to be 20 milliampere. The substitute values you get then this is the minimum value of resistance which you have to put here. Here we assume that RF equal to R. Now the resolution is the smallest input voltage which I can measure. Now here the smallest input voltage corresponds to something like, if you put all the values as 0 except the LSB as 1, that's the least significant bit. If you put it as 0, 0, 0, 0, 1, then value will get as something like this. All these will be 0 and there's a 1 there. So the value will be 5 volt by 128. Okay. Now a problem with this system is that you have to get a standard resistance in terms of the standard values, like say R, 2R. Now I have a 1K, or I can get 2K, but I can't get exact 4K or 8K. So that is a problem. And that will be a more of a problem if I scale up to a higher system. Say in case of 4-bit, I want to go to one 8-bit DA system. What do we do? So one option is use a 4-bit DA converter as a building block and use that to build up an 8K system. How do I do that? Now say for this to be an 8-bit system, as we saw in the early example, that if the current through the MSB is VR by R, then the current through the 4th lowest bit is VR by 4R. So that means if this is VR by R, VR by 2R, 4R, 8R, so this should be VR by 16R. Right? In general, if the MSB is for, say, for an n-bit system, the current due to the least significant should be VR by 2 to the n minus 1. Right? So similarly, if this is VR by, this should be VR by 16R. Again, if this is VR by 2R, this will be VR by 16 times, 1 by 16 times of that, and so on. The in general, the current through the different resistors should be of this, something like this. B3 by B7 or B2 by B6 or B0 by B4 should be 1 by 16. So the basic design reduces to something like that. You have to calculate this value of Rx, which makes the current due to this input, effective current to this input, 1 by 16 times the current due to this input. So let's see how to do it. Now what we have done is in the previous slide, say if we don't put any input here and we ground these two inputs, okay, so we get something like this. Now so this point is a virtual ground, these three resistors are grounded. So what happens is 2R, 4R, 8R are in parallel. So if we put this as Ry, that comes to 8 by 7R. So this is my R, this one, this is the Ry or the parallel common 3, and this is Rx. Now I have to find the current due to this voltage at this point. So we apply a current divider here. So the total current is V by R plus and parallel combination of these two. So it's VR by R plus parallel combination of Rx and RO. Then apply current divider between these two branches. So naturally it becomes Rx by Rx plus Ry. So this up to something like this. Now we know that the current to the first, that's a MSB one, it's VR by R. So it should be VR by 16. So we put VR by this as VR by 16 now and solve it, we get something let's Rx. In general, if we go for a, if the lower the more basic building block is of n bit, then Rx would be of the form Rx equal to n minus 1, right? That means if you have a 4-block system that we've used here and use that to scale up to an 8-bit system, then it comes to 4 minus 1, that's 2 to the 3R. Then again, if you use two block systems to develop a 4-block system, it will be 2 to the 4R. 2 minus 1, that's it will come to 4R, something like that. Now the drawbacks of this method are two. One is, as I said, it's difficult to obtain standard value of resistance satisfying the condition VR by 2R, R and 4R. And the other is, if you look carefully at the picture, the current drawn by one is VR by R, and say the 4th or 5th resistor, it becomes VR by 16R or 32 or even more. So over a point of time, they produce a differential rate of heating. Now then a resistor value changes, so the long term effect of that is they lead to errors. So we come to the next solution, that's a R to R DA converter. In this here, you see we have a ladder network like this, 2R, R, 2R, R, something like this. And this circuit, again this part is an inverting amplifier. This part can be reduced to an equivalent circuit consisting of a Thevenin voltage source and a Thevenin resistance to giving us something like this. Now we'll see that expression will come to something like that. Say for this circuit it becomes minus RF by RTH into VTH. Now the VTH will have an expression of this form. RFVR by RTH into 2 by N, and inside we have D0 2 by 0, D1 2 by 1. Again see is similar to a binary to decimal conversion like. Okay, now let's see how do we get this expression. First of all, what we do is we find the Thevenin resistance. For that, as we know, we replace all the voltage source by the short circuit. That means in this case we ground all the sources. Now then what happens, we have a network of 2R and R resistance, right? Now if you look at this one, say if we go for a Thevenin equivalent of these two 2R, so since these two are parallel, we get a resistance of R. So place this here. Now we come to this point. Again RR and 2R. So again 2R and 2R parallel. Again it gives to a resultant of R. Replace that here. Then go to this point. So if you see, no matter how many levels you go, it will always come to an effective resistance of R. RT is equal to 1. So the Thevenin resistance has to be equal to 1. Now we look at Thevenin voltage. Now first of all, say we have an input component of this. D3, D2, D1, D0 equal to 0, 0, 0, 1. Now sorry, I forgot to tell you one thing. In this expression, the input which is nearest to the op amp, that will function as the most significant bit, and that which is farthest from the source on the op amp will function the least significant bit. Let's see how. Now, first say for this combination. So this is VR and this the other sources are short circuited to ground. Now, if we find Thevenin voltage at this point, we'll see this is VR and combination of 2 R's. So the effective voltage at this point is VR by 2. And for Thevenin resistance, as we've seen earlier, these two 2R in parallel becomes R. So R plus R, it becomes 2R. So it becomes R. So the effective Thevenin equivalent of this part is a voltage of VR by 2 in series with the resistance R. Next we come to this point. So this VR by 2, again there's a 2R combination here, another 2R here. So this VR by 2 is reflected as VR by 4 here, again with an equivalent Thevenin resistance of R. Go to the next node. Again this VR by 4 is replaced by again half to VR by 8. And finally for the next stage we get a VTH equal to VR by 16. So see, the number of stages I move at each stage is divided by 2. Give me a VR by 16. Now say we look at a different combination. Say we made the second second least significant as 1. So it's 0, 0, 1, 0. That means the first one is 0 and the other ones are also 0. So the first input is 0. It is just contributes an equivalent Thevenin resistance of R. Okay. So this R and this R again becomes 2R. So we get a this the second that's a D1 bit. It is V. So V again these 2R, so it becomes V by 2 here. We move to the next state, it becomes V by 4, and the final becomes V by 8. That means since it's a second position, it moves 3 levels, we get a voltage of VR by 8. So moving in a similar manner, say we apply the principle of superposition, then for each combination of inputs we will get a contribution of VTH, say VTH for D0 position, similarly for D1, D2 and D3. This, as we saw, becomes VR by 16, this is VR by 8, this is V by 2, and this will be VR. So what happens is, see, now we'll see why we talked about the one input which is nearest to the op amp as most significant, because this has a contribution of VR, whereas this has a contribution of VR by 16. So while in the weighted resistor we were going for a division in current due to the different weighted resistors, we are having effective division of voltages. Okay. So the effective expression becomes D0 20, D1 21, D10 minus 1 for n bit, and this part, so for a 4-bit system is 16. For n bit system it comes to something like 2 by n. And LHB, that is, if we put 0 0 0 0 1, then then just this part remains, so that becomes RFR BR by 2 N. So this is my least significant bit or less bit system. Now, before concluding, we'll just look at a few jargons which are used for these converters. Now, how do you know how good is a converter, or what we call as commonly as a figure of merit? Say, if someone tells you, someone asks your parents, how good a student are you? Your figure of merit is the marks in your exams. For a car, it is either pickup or mileage, something like that. So, for DA converter, the first thing which have is resolution. Now, what's the resolution? It is defined by the smallest possible change in the output voltage as a fraction or percentage of the full scale output voltage. Now, for an 8-bit DA converter, we have 2 to 8 levels, right? So, including 0. So, basically, the range 0 to V is divided to 255 levels. So, the smallest change in the output voltage is 1 by 255 of the full scale output voltage. Therefore, the resolution is 1 by 255 or 0.44%. So, a general resolution of an n-bit system is 1 by 2 to n minus 1 into 100. Next is linearity. Now, in DA converter, say I move from input say 1 to 2 to 3. So, what should ideally happen is, say if 1 has a voltage of say 0.2 volt, then for input of 3 it should be 0.6 volt and so on. That means the input, analog input to digital output, the digital input to analog output, that curve should follow straight or linear line. Now what happens is, due to the resistance active device in circuit, it always doesn't follow. Right? Now the term linearity determines the precision with which the linear output relationship is specified. Ideally, the acceptable value is if the maximum deviation from the linearity curve is within half of LSB. Next is accuracy. The accuracy of DA converter is determined by the measure of the difference between the actual output voltage and the expected output voltage. So it is again specified as the percentage of the maximum output or the full scale output. Now say a DA converter has accuracy of 0.1% with full scale maximum output voltage of 10 volt. That means the maximum error that we can expect is 10 into 0.1%, that is 10 millivolt. Next is settling time. Now this is something we faced in our laboratory. Say you apply a digital multimeter to a circuit. What happens is, if you see the display, it fluctuates within a given range and then it finally settles to a fixed value, right? Now this is the settling time, the time required for the output to settle within plus minus half LSB of the final value. The last point we have is temperature sensitivity. Again, the circuits we are using that has an op-amp, resistance, all that, all of which are temperature sensitive devices. So naturally, if over a period of time, as the system is heated up, there may be small changes. Now the analog output voltage for any fixed digital input varies temperature, right? So the temperature sensitivity is defined as the change in output voltage from its expected value in respect to temperature over a given point. Okay. Now